Dear students, in this video I am going to discuss fixed point method, also known as iteration method or successive approximation method. Okay, so to first understand the basic idea behind this, let us take an example. So first we take one example, which is f of x is equals to e raised to the power minus x. Now we want to find the root of f of x is equals to 0. So two alternate graphical methods for determining the root of f of x is equal to e raised to the power minus x is equals to 0 are shown below. So this is the actual curve, e raised to the power minus x. When you put it 0, then you can say that this equation can be written as x is equals to e raised to the power minus x. That means this. Here e raised to the power minus x is equals to 0. This can be written as e raised to the power minus x by x. So basically there are two curves. One is this, another one is this, and they are same. That means find out the intersection point of these two. So if you draw alternately these two curves, one is this, which is nothing but f of x is equal to x. Another one is f2x is equal to e raised to the power minus x, and they are intersecting at this point. So at this point x is equals to e raised to the power minus x. So if you compare these two, so this is the root of the actual curve and they are intersecting at the same point. So this can also be treated as the root. This point can be treated as the root. So that means if you are either finding the solution of this equation or solution of this problem, converted problem, then both will provide you the same root. This is the meaning. Okay, so now here what we have done that f of x this is equal to 0 is now converted in the form of this. That means some x is equals to e raised to the power minus x. This is nothing but a new function g of x or phi of x. In some books phi of x is written. So we have already discussed this thing in our first video. Okay, so we have used that idea. So thus from these figures we can conclude that the equation f of x equal to 0 can be written as x is equal to some phi x. In our case phi of x is e raised to the power minus x, just like this, e raised to the power minus x. Okay, so this transformation can be accomplished either by algebraic manipulation or by simply adding x to both sides. Because if suppose you are not able to write down any equation in this form, suppose f of x is equals to x 0, you want to find out this root and you want to convert this problem in this form, x equal to some phi x, so just add both sides x. So x plus f of x is equals to simply x. That means this x is equals to this side, x plus f of x. This is your phi of x actually. Okay, so if problem is very complex, then you can use this idea also. So simply adding x to both sides of the original equation. Okay, now from equation number 2, that means this, we can see that it provides a formula to predict a new value of x as a function of an old value of x. That means this, what is the conversion is this phi of x. So when you put some x here, then you will get another value of x, again put that x here, then again you update you. So that means in iterative form we can say that this is nothing but phi of xk. Just substitute old value here, you will get the updated value. Again substitute it here, xk plus 1, and get xk plus 2 here. So this is the recurrence relation between xk and phi x of xk plus 1. Okay, so this is the iterative form formula, and where k is 0, 1, 2, and this is basically known as the iteration. This phi of xk is known as the iteration function, and the convergence of an iteration method, basically this is the method known as fixed point method or successive approximation. This is the formula. Okay, The convergence of an iteration method depends on the suitable choice of the function phi of x, because we are already aware about in our first video that we can write this function any problem in the form of x equal to phi x in various ways. We can treat this x is equal to f of n. Similarly, x is equal to say f2x and so on. Just like in our problem, what is our problem which we have taken here? E raised to the power minus x is equal to 0. One way is that x is equal to e raised to the power minus x. This is one way. So this is say phi 1x. Similarly, you may also treat this as, just take the logarithm. So minus x log e is equal to log x, and from here x is equals to minus log x upon log e. This is another way. This is your phi 2x, and so that's why you can write down this equation in this form in various ways. This is one way, this is another way. Okay, so this method depends upon the choice of phi of x and initial point x naught, because when you put k equal to 0, so you have x naught. X naught is the initial idea. Okay, so this method depends upon the initial idea and the choice of the function phi of x to get the solution. Okay, so suppose xk converges to the values xi, then here, so we get xi is equal to phi of xi, because this equation is exactly satisfied, because we have converted this problem f of x equal to 0 as x equal to phi of x. So if xi is the root, then xi will also satisfy this, because graphically you have seen that if xi is the root, then at this point x and this function both will be same. That's why. Okay, so this will be exactly satisfied, and hence we get this third. So now we will use this equation xk plus 1 is equal to phi of xk, and this equation just subtract third equation from 2. So what we will get? 2 minus 3 will give you xk plus 1 minus xi is equals to phi of xk minus phi of xi, which is equals to phi of, what is xk? Xk is xi plus epsilon k. Xi is the exact root and epsilon k is the error in the kth iterate, minus phi of xi. Now expand this using Taylor series. So we get in the left hand side what we have? We are having epsilon k plus 1, because this is what? This is nothing but k plus 1th iterate minus exact root. This difference is nothing but the error in the k plus 1th iterate, which is denoted by epsilon k plus 1. So this is the error. So error is this is equal to, so now expand this. So we get phi of xi plus epsilon k, phi dash xi plus epsilon k whole square by 2, phi double dash xi plus and so on minus phi of xi. Now you can cancel out this quantity with this quantity. So we get epsilon k plus 1 is equal to epsilon k phi dash xi plus epsilon k whole square by 2, phi double dash xi plus and so on. Okay, so now if you are writing this quantity, because phi is known to you, so phi dash xi is known to you, this is a constant value, so denoted by a1. Similarly, phi double dash xi is a constant value divided by 2, so this can be treated, phi dash double dash xi divided by 2 can be written as a2. Okay, so this is, so the equation can be rewritten as epsilon k plus 1 is equal to a1 epsilon k plus a2 epsilon k whole square plus higher order terms, order of epsilon k cube, where k is 0, 1 and 2. What is epsilon k? Epsilon k is the error in the kth iterate, which is nothing but xk minus xi. What is a1? A1 is this phi dash xi. What is a2? A2 is this quantity 1 by 2 phi double dash xi and so on. So now with the help of this equation you can make number of methods. For example, if you want to convert linear, because this will provide you, actually this is the error equation. So if you want to make a linear method, so your a2 will be 0, and because for linearity means what, a2 and higher order terms will be 0. If you want to make second order convergence method, then your a1 should be 0, तब आपका a1 0 हो जाना चाहिए, एंड a2 शुड बी ए नॉन जीरो क्वांटिटी, सो दैट यू विल गेट अ सेकेंड ऑर्डर मेथड. तो आप अलग अलग ऑर्डर के मेथड बना सकते हैं, लीनियर ऑर्डर बना सकते हैं, सेकेंड ऑर्डर का मेथड बना सकते हैं. ओके, सो दैट्स वाई. So now if you are for example, if you are writing the first order method, then obviously a1 should be a non-zero quantity. a1 should be a non-zero quantity, and then neglecting higher order terms, then what we will have, epsilon k plus 1 is equal to a1 epsilon k. तो हम लीनियर मेथड बना रहे हैं, इसका मतलब a2 और हायर ऑर्डर टर्म्स को नेग्लेक्ट कर दिया, सो वी गेट दिस इक्वेशन. So now put k equal to 0 1 2, so what we will have, epsilon 1 is a1 epsilon naught, epsilon 2 is a1 epsilon 1, but epsilon 1 is what, a1 epsilon naught, so that's why we have a1 square epsilon naught. Similarly a3 will be a1 epsilon 2, but epsilon 2 is a1 whole square epsilon naught, so substitute it here, so what we will have, a1 cube epsilon naught. So in general epsilon k is a1 raised to the power k epsilon naught. Okay, so when if a1, the magnitude of a1 is less than 1 and epsilon naught is not very large, then the iteration method this converges. बिकॉज अगर a1 1 से ग्रेटर होगा और k की पावर बढ़ती रहेगी तो ये क्वांटिटी बढ़ती रहेगी रेगुलरली, एंड हैंस दिस विल टेंड टू इनफाइनाइट, और ये मेथड कन्वर्ज नहीं करेगा. कन्वर्जेंस का क्या तभी कन्वर्ज कर सकते हैं जब आपकी एरर जीरो की तरफ टेंड हो. सो योर एरर शुड बी जीरो as k varies, and this is only possible when the magnitude of a1 is less than 1, so that your k, when k increases, when k is increases, a1 raised to the power k decreases rapidly, and this is only possible when the magnitude of a1 is less than 1. Okay, so now for the convergence of the method, the magnitude of a1 should be less than 1. Okay, and this method has linear convergence. So now if you will see here, we have a criteria. If suppose you are, this is the interval on the real line, and you are saying that this shows the a1 actually. Okay, a1. So here the magnitude of a1 is less than 1. So that's why what? You are covering the interval from -1 to actually 1. This interval, you are covering the interval this. -1 to 1, because in this interval magnitude of a1 is less than 1. Fine. Now so we can divide the interval into 4 parts. Here is 0, so one part is this, say denoted by 1, another is this denoted by say 2, then we are having third part this, and then we are having this part, fourth one. Okay, now for for this part, here a1 is in between 0 and 1. For this part a1 is in between -1 and 0. For this part, third part, a1 is greater than 1 or equal to 1, and here a1 is less than -1. Okay, or equal to, here is equality. Okay, so now we will discuss these 4 parts. Now if you are taking the first part, so your a1 is in between 0 and 1, and in that case we have this type of convergence, staircase convergence, because in this interval, that means in this interval from here to here, from -1 to 1, method converges, here converges. This is the condition of convergence. That's why. So if you are taking this, so what happens? Suppose you have started with x naught. Then what is the formula? Formula is this. Xk plus 1 is equals to phi of xk. This is the formula which we have developed in this method. So when you start with x naught, this is the curve phi of xk, phi of x. This is the x. This is x, because what is the procedure? If you have seen in this, This is x, this is your actually the phi of x. This is your phi of x. Okay, so in this case, this is your phi of x, for example. This is your x. This is x. This is phi of x. So now they are in, these two curve intersects at this point, and this is the root xi. This is the root xi. Okay. So now to start the method, this method, if you have started with x naught, so this is your point x naught. So at x naught, find out phi of x, because here we have phi of x. So find out this. So this will provide you the phi of x. But you will see that phi of x is exactly equal to x. Exactly equal to x. And hence, at this moment, what will be the x? X, this is the x curve. So since this, so that's why we are drawing this horizontal line. Why we have taken horizontal line? Because at this moment, this height and this height both are same. That's why this equality holds. So this height and this height both are same. So that's why we have drawn the horizontal line. So now we have started with this point. Then we are moving horizontal line due to this equation. And at this moment again, now at this is nothing but your x1 actually. This point is your x1. Now x1, put phi of x1 and get x2. So at this moment, if you are finding the value of phi, so what we will have? Phi of x1. Phi of x1 means this point. So basically we are moving from here to here. And now again, using this equation, again draw the horizontal line. So this will provide you third iterate this. This is basically the x2 sorry. And this at x2, find out phi of x2. So this is the phi of x2. Again draw the horizontal line, and then you are getting x3 and so on. So you will see that you are moving towards xi in staircase, just like stairs. So that's why this is known as staircase solution. Okay. Now when we are taking the second case means this, from -1 to 0. Okay, what is the meaning of this? 0 to 1 means, what is a1 actually? A1 is this. If you will see phi dash xi. So phi dash xi is here. The derivative is actually in between 0 and 1. This is the meaning. That means tangent, the value of the tangent, the slope is in between 0 and 1. Here the slope is in between -1 and 0. Fine. So here you will see that, if you will see that here the slope is increasing. That's why in between 0 and 1. However, here if you will see, the value of the slope is in between -1 and 0. That means decreasing. That's why we are having this type of curve. This is the reason why we have selected this curve. Because in this case, your slope, this slope is in between 0 and 1. That means increasing slope. However, here slope is in between -1 and 0. Because a1 is what? Phi dash xi. So slope at point xi is negative from -1 to 0. That means decreasing. That's why we have selected this curve. This is the reason. Okay. Then again, this is x. This is phi of x intersecting at this point. So this is xi. So we have started with the again same strategy. Started from this point. Find out phi of x naught. And at the same point, draw the horizontal line. This intersect this curve, and this will be basically your x1. Now again find out the value of the phi. So at x1, so this will be the phi of x1. Again draw the horizontal line, and this will intersect you this, and this is basically your x2. So you will see that x0, x1, x2, then you are getting this point x3 and so on. So ultimately you are moving in the spiral. This is just nothing but a spiral. So this is a spiral case solution. Okay. Now the third one, when you are opting the third one, if your a1 is greater than 1, that means strongly or strictly increasing. That's why we are having almost same type of pattern, but strictly increasing. That's why more slope, more higher slope. That's why we have selected this as a curve. This is x, this is the curve. So when you started from here, then you will see that we are moving. This is phi of x naught. We have started with this. This is the exact root. We have started with very close point. X naught is very close to xi. We have taken this. We have started with this. Then take the horizontal line. So you will see that you are basically moving away from the root. You are moving away from the root. Then after second iteration you will reach to this, and so you will see that slowly you are moving away from the root, and that's why divergence. This is the divergence case. Okay, so when a1 is greater than 1, divergence case. And this is staircase divergence. This is staircase divergence. Now in the fourth we have spiral case divergence. So here the curve is this is your phi of x, this is your x. So we have started with this is the intersection point, this is phi. Here we are taking a1 is less than -1. Okay, fourth case. So now that's why slope is decreasing. So if you will see that here we have started this very close point. So here, then this is phi of x naught. Now draw the horizontal line. This is basically your x1. Then find out the value of the function at x1, which is nothing but this. Then again draw the horizontal line. So this will intersect at x, this curve x at this point. So this will provide you the x2. So you are saying that slowly in spiral way you are moving away outer side, and hence this is again the divergence case, but in spiral case, so this is spiral case divergence. So these are the total 4 cases. 2 are for the convergence, 2 are for the divergence. Okay, I think you understand this. Now we have a theorem based on this convergence or divergence for this method. So a sufficient condition on phi of x for the convergence is given by the following theorem. What is the condition? Condition is obviously this: phi dash xi, this a1 should be less than, what is a1? A1 means this. So basically what is the condition? Condition is that phi dash xi or phi dash x in general, this should be less than 1, and this will provide you the basically the selection of phi. What should be the suitable choice of phi? You can select this phi with the help of this theorem. Okay, so that your method will converge. So if phi of x is continuous function in some interval a to b that contains the root, and phi dash x is less than c, where c is less than 1 in this interval, then for any choice of x naught from in the closed interval a to b, the sequence xk determined from this xk plus 1 is equal to phi of xk converges to the root xi of x is equal to phi of x. So this condition is main. So this condition basically inspired by this. Okay, because what is a1? A1 is phi dash xi. So here in general phi dash x should be less than 1. Okay, so if you select this phi which satisfy this condition in this interval, then obviously that phi will provide you the convergence to the root xi. Your problem will have a solution. Okay, so now proof. The exact solution xi satisfies the equation this xi is equal to phi of xi. So we have now subtract this equation from this equation. This is the, because this true root or exact root will satisfy this equation. So we have this equation, and this is the condition. So now when you subtract this equation from this, so we have this equation. Xi is equal to xk plus 1 is equal to phi of xi minus phi of xk. Okay, now multiply and divide by xi minus xk. So xi minus xk multiplied and divide in the right hand side, and this is phi of xi minus phi of xk. What is this? This is nothing but derivative. derivative. In real analysis you have already studied about this derivative condition. Okay, so by using mean value theorem, phi minus xk plus 1 is equal to xi minus xk. This is nothing but phi dash xi k. Here xi k varies from xk to xi in this interval. Your xi k is any point in the interval from xk to xi. Okay, we have already studied, you have already studied this in real analysis when differentiability is discussed. Okay, so let us see that. So what is this in the left hand side? This is nothing but the error in k plus 1th iterate. So epsilon k plus 1 is epsilon k phi dash epsilon xi k. So now here, okay, so what you will do, just substitute the value of xi k or epsilon k plus 1 is this. So if you just find out epsilon k from here, what you will have, just reduce the index by 1. So what you will have, epsilon k is equals to, here you will have epsilon k minus 1 and then phi dash xi k minus 1. Substitute this value epsilon k here. So what you will get, epsilon k minus 1 phi dash xi k minus 1, and this is here phi dash xi k. Again substitute the value of this. So from here epsilon k minus 1 is epsilon k minus 2 phi dash xi k minus 2. Substitute this value herein. Okay, and slowly this index will reduce and move up to epsilon naught. लास्ट पॉइंट होगा एप्सिलॉन नॉट बिकॉज के स्टार्ट्स फ्रॉम जीरो. तो आपका इंडेक्स धीरे धीरे घटता रहेगा एंड इन द लास्ट, और ये मल्टीप्लाई होते रहेंगे. सो अल्टीमेटली यू विल हैव एप्सिलॉन नॉट phi dash xi k minus 1 and so on, and last phi dash xi naught. Okay, and here we have this condition. So epsilon naught, here epsilon naught will be in between x naught and xi. Xi1 is in between x1 and xi k minus 1 in between xk minus 1 and xi k is in between xk and xi. Okay, so if phi dash xi r is less than c, if this condition holds where r is 0 1 2 k, then the magnitude of epsilon k plus 1 is less than equal to what? The magnitude of this quantity is equal to magnitude of this quantity. But here this is given that this quantity is less than c, this quantity is less than c, this quantity is less than c. So ultimately c f less than equal to c raised to the power k plus 1, because these are total k plus 1 quantities. K plus 1 magnitude of epsilon naught. Okay, so if c is less than 1, if this quantity, this is already given to you, if this quantity is less than 1, then this right hand side tends to 0, and hence we can say that error becomes 0, and hence we can say that method converges. Okay, so this is the proof of this theorem. I think you understand. Now we will take one example to illustrate the method. So find the root of the equation. This we have already taken this equation earlier. X cube minus 5x plus 1 is equal to 0. Using linear iteration method, correct up to 5 places. Okay, so what is f of x? F of x is x cube minus 5x plus 1. This is your function. So this should be 0, so that we have this equation. So root lies in the interval 0 to 1. You can easily examine by intermediate value theorem that root lies in the interval 0 to 1. So now we write the given equation as this. Just write down this in this form. So this f of x is equal to 0. This is the actual problem, and now this is converted into x equal to phi of x. And you can convert this into this form in number of ways. One way is this. Just take this 5x in the right hand side or left hand side, and remaining term x cube plus 1 in the another side, and then divide by 5. So we get x equal to 1 by 5, 1 plus x cube. This is your phi of x. Okay, so now you just examine the condition with the help of this theorem. So what is the derivative? What is phi of x? Phi of x is 1 plus x cube by 5. Just differentiate this. So derivative is 3x square by 5. Find the magnitude. So magnitude is obviously less than 1. Why? Because what we have here, we have this. We have phi of x is equals to 1 by 5, 1 plus x cube. Just to differentiate this, so we get 3x square by 5. So now find the magnitude. So magnitude is 3x square by 5. That means 3 by 5 magnitude of x whole square. But x is laying, the interval is, the domain is in between 0 and 1. So obviously this quantity is less than 1. This quantity is less than 1 and its square is also less than 1. And 3 by 5 is also less than 1. So ultimately less than 1. So condition holds in this interval. Okay. That's why this is less than 1 in the interval 0 to 1. Then the iteration method converges, and you can now in iteration form you can write this as this left hand side x is written as xk plus 1, and this right hand side one, this is written as 1 by 5 1 plus xk cube. Okay, so that you will have the required iteration formula of this form. Okay, so this is the formula. This is your phi of xk, where k is 0 1 2 and 3. And now start your method. So here we have 3 columns in tabular form. This is kth iteration number column. This is iterate xk and then xk plus 1. Okay, so start from initial value k is 0. Then x naught is selected as say 0.5. 0.5 is basically the interval. This is your interval 0 to 1. So we have selected the midpoint, actually midpoint as your x naught. So when you put a 0.5 here, then with the help of this formula 1 by 5 1 plus x naught cube. So put x naught here. So 1 plus x naught cube divide by 5. This will provide you x1. So here is x1, this. So now copy this here in as it is copy, and now iteration number is 1. Okay, and then find out x2 with the help of same formula. So this is your x1. Again copy it here and then find out x2 and correct up to 5 decimal places tak hame chahiye. So you will see that both are not same up to 5 decimal places. So that's why find out x3. So this is your x3. Again they are not same up to 5 decimal places. So again find out x5. So this is the x5. Now you will see that x4 and x5 both are same up to 5 decimal places, and that's why this is the solution. Okay, again another way is, suppose you are selecting this as your formula, because here what we have done it here. What is our function? If you will see, we have x cube minus 5x plus 1 is equal to 0. Okay, so here is this. Now in the second choice, suppose you are selecting this. This is also good, no problem, ये तो हो चुका. But suppose you are selecting another function. कोई student ये वाला opt करता है, कोई ये हो सकता है. So it may be possible. So suppose you are opting the second choice. Then what you can do? You just take x common from first two terms. So you will have x square minus 5 is equal to minus 1, and then x is equal to minus 1 upon x square minus 5. So this is now your phi. This is your phi. So this is written here. So 1 by 5 minus x square is phi of x. Now to check the convergence, first differentiate this function. So phi dash x is minus 2x by 5 minus x square whole square. Again the magnitude of this is less than 1 in the interval 0 to 1. Again using the same logic. So this is a convergence formula. So again you can apply this. Again started with this. So here I am not writing this column, I am directly writing this one here. Okay, so here we have started with x naught is equal to 0.5. Then this is your x1. This is your x1. Okay, then put it here and then find out x2. So this is your x2. This is your x3. This is your x4. This is your x5. Again you are getting the same solution. Okay, now suppose we are taking another option. Just like x cube can be written as x into x square. So just take this x in the left hand side and the remaining term in the right hand side, so we get this phi of x. But when you differentiate this phi dash x, so ultimately you will get 2 minus 5x by x cube. And this is basically what? About, you will see numerator part. When you put x in between 0 and 1, you will see that this quantity, the magnitude is always greater than 1. That means phi dash x is greater than 1, so not a feasible choice. So if you are trying to solve your problem with the help of this formula, then you will get the divergence. Your method will diverge, and the reason is that the magnitude of the derivative of this function in the interval 0 to 1 is greater than 1. That's why. So this is not the feasible choice. So either you can take first option or second option. They will be better, or maybe any other option, but this third option is not good. Okay. Similarly, we have second example. So you have to do yourself second example. So problem is cos x minus x e raised to the power x is 0. Okay. So this can be written in the form of function iterative formula as x equal to phi of x. So from here, just take this x in the left hand side and cos x divided by e raised to the power x in the right hand side. So this is your phi of x. This is your phi of x. Okay, so now first check the convergence. So just take the derivative of this function is minus sin x plus cos x divided by e raised to the power x, and in this interval 0 to 1, the magnitude of this function is, because the magnitude of this is always less than 1 and has a convergence formula. So a convergence formula, so that's why we have taken this, we have solved this problem. So we have started with 0.5 and then we have constructed this table. So this is k iteration number and this is the iterate xk plus 1 is phi of xk. So started with 0.5. So put phi of 0.5, we get x1, then x2, then x3 and so on. So up to 7 we have written here, then from 8 to 15 we have written here, and ultimately we will get the solution in 20 iterations. So these are total 20 iterations. So solution is, because we need a solution, if you will see here, correct up to third decimal places. Correct up to third decimal places. So after this 20, 19 and 20, if you compare 19 and 20 here, 0.517, 0.517. So both are same up to third decimal places. That's why this is the solution, which is correct up to third decimal places. Okay, that's why we have stopped it here. This is the reason. Okay. So this is 0.517 is the solution. So this is the successive approximation method. Okay. So now your first unit is over. Now from the next lecture, we will start solution of system of nonlinear equations. Here we will have three methods: Newton-Raphson method, quasi-Newton method and Broyden method. And we will take these methods one by one. Okay. Thank you.